Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last week, where we were talking about the mechanical force that is produced on a current carrying conductor placed in an external magnetic field and on the ability of this mechanical force to produce a rotational effect on an electric motor. And we had used this diagram to describe that effect. So for example, if we have some fulcrum which has a pivot here and which can rotate, we had shown that any force which is applied on this fulcrum can be decomposed into two components, one along the fulcrum and the other orthogonal to it. And we saw that the force which is orthogonal to it and which is along the tangent has the maximum ability to produce the rotational effect. And this is in general itself. So not only do we have to see the direction in which the mechanical force is produced, but we also have to make sure we also have to decompose the force into components that are tangential to the actual, or I would say tangential to the path of rotation, right? So in this lecture, I'm going to talk about how we're going to bring all these concepts together in the context of an electrical motor. And why is all this important? Why is the nature, direction of force important? Why is it important to decompose the force? Why are these two components of force important in an electrical motor, and what kind of effects they produce, right? So we'll talk about that briefly in this lecture and maybe also in the next few lectures. So as before starting the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length online courses that you can find on my website, pythonpowerelectronics.com. So this is the homepage of this project, where you'll find almost everything related to this project. And on the very first page, there are these 4 buttons, out of which if you click on the button Learn, it'll take you to the list of courses. So as of now, I have 5 courses. The very first course is Simulating Power Electronic Circuits using Python. And in this, I talk about the basics of how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use Python and packages such as the Signal package within SciPy to design and analyze filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components such as inductors, coupled inductors, and transformers. And the fourth course is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python Control package to design and analyze controllers for power engineering applications, with the specific example of a single phase inverter connected to a single phase grid. And the last course is a free or motivational course which is called Why Specialize in Power Electronics, and this is targeted more towards either undergraduate students or high school students who have not yet chosen their domain of specialization. And this course is to describe some of the challenges and power opportunities available in power electronics so that young students can choose power electronics as their domain of specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy. If you click on the link for any of them, it will take you to the course. The link for this page is provided in the description of this video. If you're interested, please do check it out. So with this, let me return back to my lecture. So this is where we are in talking about the force. Now let's bring this concept into a motor. So before we actually go to the diagram, let me talk about the actual diagram, right? Because it's nice to bring the actual diagram once in a while rather than some simplified concepts. So as I've already said, this is a motor. You can find this, you can just Google single phase induction motor. This is a single phase induction motor. It's been taken apart in a very nice way so that you can see all the different parts. The outer part, as we have already talked about, is a stator, and this stator has stator windings all around it. So this, you see this solid part here, this is actually stator windings all around it. This stator is supplied usually by either a 240 volt 50 hertz AC, or could be a 120 volt 60 hertz AC, depending on which part of the world you live in. And because of that, a current flows in the stator windings, and that current produces a magnetic field. Now this rotor is kind of mounted inside this stator, of course leaving an air gap, because otherwise there won't be any rotation. But this is mounted within this stator using these endpoints. You see, this is how it is mounted. And this rotor, in this case, this motor is a squirrel cage induction motor, so which means the rotor comprises of rotor bars that are short circuited on both ends, right? So because of the flux produced by the stator, a current will be induced in the rotor, and therefore this current that is flowing in these rotor bars is going to interact with the external magnetic field, and a force is going to be produced on it, and therefore this rotor is going to rotate, right? This is a simplified working principle. Now let's take this concept and go back to our diagram. Actually, I have another diagram. Yeah, this is a diagram of the motor. So we have taken a very simplified representation of the induction motor, where we said that all the stator windings are on on two slots diametrically opposite each other, right? This is not the case. In reality, the stator windings are all around the circumference of the stator. Similarly, we had also said that all the rotor bars are concentrated on just two slots, or rather two positions diametrically opposite each other. Now, this makes it easy to visualize the force and the nature of magnetic flux and things like that, but in reality, this is not the case, right? So, now we had also said that depending on if we choose some direction of current for the conductors in the upper slot and another direction of current for the conductors in the lower slot, we can use the right hand thumb rule to determine the nature of magnetic flux, right? So, if we choose some direction, and if we say that this magnetic flux here is in the counterclockwise direction, in the lower slot it will be in the clockwise direction, because they are always opposite to each other. Now, this magnetic flux links with the rotor, and therefore it induces a voltage in the rotor bars that causes a current to flow in the rotor. And as you can see, because of this, very clearly there is now a current carrying conductor placed in an external magnetic field, and therefore a force is produced here. Now, and we had also seen that this force, we can use Fleming's left hand rule to determine the direction of the force, right? We can use Fleming's left hand rule to determine the direction of force, and we saw that we see a mechanical force in this direction for these two slots, which causes the rotor to rotate in the counterclockwise direction. Now, the question therefore arises is, how do we arrive at this? For example, now here we had talked about this to some extent. We are producing this coil here, for example. Let us say the current in these conductors is flowing into or rather you can see it is flowing out of the screen, right? So the current is coming out of the screen. Now, if we use right hand thumb rule, that is, we grab all the conductors with our right hand while using the thumb to point in the direction of the current, then the direction in which the fingers encircle the conductors will be the direction of the magnetic lines of force. So which means the magnetic lines of force will be concentric lines in the counterclockwise direction. Now, let us look at the actual path of the magnetic lines of force. The path of the magnetic lines of force lies in three parts. One is through the stator, one is through the air gap, and the other is through the rotor. The stator consists of a metallic path, right? This stator usually comprises of some form of laminated iron or an alloy of iron. Similarly, the rotor also consists of laminated iron or some alloy of iron. So these metallic parts have a very high permeability to magnetic lines of force as opposed to air. Typically, the relative permeability of metal like iron or laminated iron is close to 1000 times the permeability of air. So, magnetic lines of force will pass through a metallic medium 1000 times more easily than it will pass through air. Now, if you just take a simple look, the number 1000 is pretty huge. So therefore, one can say that in this path, that is through the stator, through the air gap, through the rotor, and then back again, the main reluctance to this magnetic lines of force is provided by the air gap, right? The reluctance provided by the magnetic mediums is negligible. So we don't really care about this path where the magnetic lines of force flow. We are only concerned with this in the air gap because that is the real reluctance that is offered to the magnetic lines of force. Now the question here is, I have drawn this just as concentric lines, but in reality, what will it be? For example, let's take a look. If magnetic lines of force would flow, right, in this through a path, right, through any path, then the question is, what path will they choose, right? Now, just like water or electricity, magnetic lines of force will choose the path of least reluctance, right? Water will flow through the path of least resistance. Current will also flow through the path of least resistance. In the same way, magnetic lines of force will also try to pass through a path of least reluctance. So now the question is, if we forget about whatever is the reluctance of these magnetic mediums, metallic mediums, and we concentrate only on the air, the question then arises, what is the path of least reluctance? The path of least reluctance is the path with the least length, right? That is, the path with the least length is the path of least reluctance. And the path of which the least length lies along the radius, right? If we take a look at this, all these paths which I've drawn, they are actually not the real paths. Why? Because they are much longer. If I were to compare this, let me draw here. If I were to compare this with this, which is longer? Obviously, this is longer than this. Why? Because this lies along the radius, right? I am drawing this line along the radius, whereas this line is not along the radius. This is some random path through a circle. And therefore, if we actually take a look, then in that case, the flux will not flow in this manner, but will rather flow through the path of least resistance here. So if I were to draw the lines of flux, they would be flowing in this direction. I'm just going to draw a few, not many. So these are the lines in which, roughly assume, just approximately they're going to pass through the center. So they are along the radius, right? So one can say that all these lines of flux are going to pass through the radius, and therefore this is the path of least reluctance, right? So now the question then arises, what is the significance of this? The significance of this is, let me just delete this one line and let me draw another. Okay, there is already. So this is also a line of magnetic force, a magnetic line of force rather, right? Now the question is, all these have their direction here because we are saying that this current is flowing out of the screen, and therefore all these lines of force are in the counterclockwise direction. And if they are in the counterclockwise direction, then in that case, their direction here is in this manner. So I'm just drawing some arrows. And if we take a look now, right, we have now a magnetic line of force which is along the radius, which is along the radius at which this rotor slot lies, And therefore, if we apply Fleming's left-hand rule, quite obviously, right, and also here of course we need to assume a certain direction of current here, right, in the rotor. Technically speaking, we can actually deduce it, because we can say that if this current were increasing, right, the magnetic force were increasing in strength, then in that case this rotor will be producing a magnetic field which will oppose the increasing magnetic field, and therefore we can deduce the direction of current. But let's not go into that. Let's just assume, simply speaking, a direction of current for the rotor, and that direction of current of the rotor, let's say, is inside the screen. Therefore, if it were inside the screen, and if you use Fleming's left-hand rule, that is, if you hold your left hand such that the forefinger was in the direction of the magnetic line of force, the middle finger is in the direction of current, which is inside the screen, then this thumb points in the direction of the mechanical force, which is in this direction, right? Okay. Now the question here is, and this is a very interesting question, is that if we take a look, because the Fleming's left-hand rule clearly states that all of them will be at 90 degrees to each other, the mechanical force is at 90 degrees to the radius, and that means it is along the tangent, right? This mechanical force is along the tangent. And if we go back to our other diagram, and we will see, if we are producing a force purely along the tangent, this force has the maximum ability to make the rotor rotate, right? So incidentally, and therefore very interestingly, because of this design of the motor and because of the nature of which magnetic lines of force choose the path of least reluctance, we are now producing a mechanical force which has the maximum ability to make this rotor rotate. Now the question arises, of course, can you say, will this always happen? And the answer to that is no, it will not. Right? Now this lecture has gotten pretty long, so I'm going to stop here. But in the next lecture, I will also talk about how some non-idealities in the magnetic lines of force will produce other components of force, and those components of force will produce certain undesirable effects such as vibration in motors, right? So with this, I'm going to stop this lecture, but the main idea behind this lecture was to talk about why all these things are important. Why is it important that we are applying Fleming's left-hand rule? Why is it important that we are considering how a force produces a torque? So how a force produces a torque, and that is that any force can be decomposed into two components, and it is the component along the tangent that is actually responsible for producing a torque. So with this, I'm going to end this lecture. If you have any doubts, please do either post in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this lecture. Thank you so much for listening, and goodbye for now.